Welcome to the Explainer. Hey, have you ever pressed a button in a PLC program and instead of the action happening once, it happens like 1,000 times? Yeah, today we're going to solve that. We're diving deep into the one-shot signal. It's the absolute bedrock tool for making an action happen exactly once.
So here's how we're going to break it all down. First, we'll look at this repeating problem. Then we'll dig into the PLC scan cycle to see where it comes from. And after that, we get to meet the solution, the rising and falling edge triggers. And finally, we'll wrap up with why this is, and I mean this, a complete game changer for your code.
All right, let's kick things off. First up, let's frame the exact puzzle that we're trying to solve here. Trust me, it's something every single PLC programmer runs into.
I know, it sounds like a silly question, right? Obviously, just once. But here's the thing. In the world of a programmable logic controller, which thinks in milliseconds, what feels like a quick single press to you and me looks like a very, very long on signal.
And this is where it gets messy. Imagine an operator just holds a button down for half a second. To the PLC, with its crazy fast scan time, it sees the input is true and executes the action. Then it scans again, like a microsecond later, sees it's still true and runs the action again, and again, and again, literally thousands of times before that button is even let go. And that can cause some huge, unexpected problems.
But here's the real kicker. This isn't a bug, it's a feature. The whole problem is actually baked right into the fundamental way that PLCs are designed to work. It's all about their continuous, looping process. And that process is called the scan cycle. The best way to think of it is like the PLC's heartbeat. It's just this relentless, constant loop, and it's the foundation for how it sees and interacts with the world.
The whole thing is actually pretty simple, but it happens incredibly fast. So in every single one of these cycles, the PLC reads the status of all its inputs. Then it runs your entire program, top to bottom. Then it updates all the outputs based on what your logic decided. And then, boom, it starts the whole thing over again immediately.
And this slide, this right here, really gets to the heart of the matter. See, our standard PLCs, the ones under IEC 61131-3, they're cyclic. They just live in this constant loop, rechecking everything, all the time. They don't have built-in events like some other systems, say from the IEC 61499 standard, where the logic only runs when something actually changes. So our challenge is to create our own event. We need to find a way to spot that one single moment of change in a system that only knows how to loop.
So, how in the world do we do that? How do we create an event? Well, let me introduce you to the hero of our story, the standard function block that was literally designed to give us event-driven power in a cyclic world.
You know, this doorbell analogy is just perfect. Think about it. A lamp switch is a continuous signal. As long as that switch is on, the light stays on. But a doorbell, that's a one-shot signal. You press it, it rings once, and holding your finger on it doesn't make it keep ringing. We need to turn our button into a doorbell.
And this is the tool for the job, the R-trig, or rising edge trigger. It's a standard function block defined right in the IEC 6113-3 standard. Its entire purpose in life is to watch one signal, and the very instant that signal rises from false to true, it gives us a clean, single pulse that lasts for exactly one scan cycle. That's it. So how does it pull this off? Well, the mechanism behind it is incredibly simple, but it's also kind of brilliant. Come on, let's peek under the hood.
Okay, let's walk through this table scan by scan, because this is where you see the magic happen. So, in scan cycle 1, everything's off, no big deal. But now watch what happens in cycle 2. The input CLK goes true. The block checks its internal memory, sees the input was false before, and bam, it fires the output Q. But only for this one scan, because look at cycle 3. The input is still true, but now the block has updated its memory. It remembers it was on last time, so the output turns off and it stays off. And that right there is our one-shot pulse.
This right here is the secret sauce, the logic pulled straight from the standard itself. All it's saying is this: the output Q is only true if the input CLK is true right now, and its little internal memory bit M was not true on the last scan.
That's the key. After it does that check, it then updates its memory M to match whatever the input is now. That internal memory is everything. It's how the block remembers the past, so it can spot the change in the present.
Okay, that's cool, but what if you don't care about when the button is pressed? What if you care about when it's released? Well, don't worry, the standard has you covered there too.
Meet the F-trig, or falling edge trigger. It's the perfect twin to the R-trig. It does the exact same thing, but in reverse. It's watching for a signal to go from true down to false. This gives you that same precise, one-shot pulse, but it happens at the moment of release. This is perfect for stuff like latching a value or triggering an action right when a process is finished.
Okay, so we've seen the problem, and we've met the solution. But let's just zoom out for a second. Why does getting this concept, mastering edge detection, matter so much for anybody working with PLCs?
Well, it's because this is how we move from just simple, reactive logic to precise, intentional control. It's how you build things like toggles, counters, and all sorts of other stateful logic. By turning a continuous state into a single, momentary event, we make sure our machines behave predictably, safely, and efficiently. They do exactly what we want, when we want them to. It's truly a fundamental building block for almost every advanced function you can think of.
Ultimately, this is a huge shift in thinking. You stop just asking, is this on or off? And you start asking, wait, when did this turn on, or when did this turn off? You're not just reading states anymore. You're capturing moments in time. And that control over the when is the real essence of powerful, reliable automation.